live as well. Awesome. Okay. Alberta 3D printing, 3D Monkey. Good to see you. I'm glad we caught some of our European crowd today. Welcome everybody. Brian Vines, the Pun Master General. Always good to see you, my friend. Hopefully, we're doing the best we can here. We're going to say a little prayer to the tech gods. Make sure that everything works out okay. We're going to try to simulcast both on YouTube and in Twitter Spaces. I wanted this opportunity for people that maybe want to more discreetly tune in to be able to maybe just do a listen on the Twitter, and anybody that wants to be able to see all the visual aids and whatnot too. I'll post a link to the YouTube link if you want to follow us there. Let's see here. Hold on. Let me just make sure. Apologize as we get everything ironed out, and we'll get started. All right. I think I'm seeing live. I'm seeing audio. I'm seeing people on the Twitters. I apologize if you're tuning in on the YouTube. It does say that we're live. At the moment, I do see people starting to show up in the chat. Thank you so much. I apologize if there's a little bit of an echo. Like I said, we're trying to do this simulcast thing. This is kind of our first attempt at this. So welcome, everybody. I'll try to keep an eye on the chat, but we're kind of juggling a lot of things here this morning, and I really want this to be more about the meat and potatoes of the conversation. So just to give you guys a quick sense of what we're going for, I have been talking to Andrew over the course of the last couple of weeks about just a lot of these questions that I've had in 3D printing, specifically as they relate to humidity and what it is doing to my filament, and am I on the clock the minute that I open it up? Is it going bad? What's really happening? And so we're going to talk about that today, but we're going to dive a little bit deeper than I think most of you have probably ever gone before, and hopefully we're going to settle some maybe some misconceptions that you might have, or maybe, give you some ideas that you hadn't quite seen before. So without further ado, for any of you who haven't met Andrew Mayhall, he is one of the brains behind 3DGloop, but I will let him speak for himself. Andrew, tell us, who are you and what do you do? It's the only glue I use, my friend. Yeah. And what's your educational background? Tell us about your experience. Why would I want to talk to you about this? And real quick, Andrew, on your Twitter, sorry guys, I apologize for this. You have to turn your mic on. Everybody's saying they're just lip reading. I thank you everybody in the chat. I'm sorry, we're ironing out what simulcasting actually is going to look like. Welcome everybody that's coming in. Uh, are all right. Do we have him? Do we have him now? Can- Okay, I can tell you're coming through. Yeah, yeah. I appreciate that. All right, give us a thumbs up in the YouTube chat if you guys can hear it on. I think we might have lost a couple Twitter people because uh, we're rookie ball getting started here on this, but hopefully it's a little bit better. Okay, so everybody, welcome. I'm Pooch. You may know me as Repcord on all the things. I've been 3D printing for just about 7 years now, and the basis of this conversation is like, as much as I think I know about 3D printing, the deeper I dive into trying to inform creating better product and what's going on with filament and all that stuff, the more I realize I don't know. And that led me to kind of seek out more information, and I wanted to talk to somebody with a background like Andrew's in chemistry and in science and stuff like that to really get down to the nitty gritty more of like what's going on, what's happening at the molecular level with my filament, like how concerned do I need to be, I talked about like there's some questions that I want answers to, like why is my filament getting brittle, and am I on the clock? Like I said, the minute I open the bag that it comes from, is the vacuum seal doing anything? Like all these things. So we're gonna get into that today. Everybody still says no on your audio. Link for Twitter. You guys still not hearing any audio on Andrew's side. So does it say mic is on your bottom mic? No sound. People are saying they can only hear me. This is not going to go well if how is it that we test, and we test more, and hold on. How about this, guys?
So it looks like my audio is not coming through the stream on your end. Oh, okay. Yeah.
I'll try both of these. So I'm talking, Andrew's talking. Are we clipping?
Testing.
Oh no, it's switched. Now nobody. Wait, I got a yay. We got a yay? We got no Pooch on here now? I don't know.
Now you can't hear Pooch.
Womp, womp, womp. Yay for technology. Well, I don't know. I say we progress. I've got my mic on. I'm seeing levels here, and I'm hearing levels, and I'm seeing levels on yours as well. So let's just dive in, and hopefully it catches up. And if we lose people, well, we'll post the recording and see if we can give it another go another time. So Andrew, let's start with like what is humidity? I've got one of these guys, right? And I think you guys have all seen these little hygrometers, and it tells me it's 44% humidity in here, and it's 17 degrees Celsius, which for people that want the freedom units is 63.8. A little cold in here. That's why I'm wearing a sweater. But we see these all the time, and this is telling us what exactly?
Well, yeah. So relative humidity is basically a measure of the water vapor relative to the temperature of the air, right? So there's water vapor pretty much everywhere. Water is the life of everything, and so it kind of infects I guess literally everything. So there's a couple ways to measure humidity. One of the most common ways is relative humidity, simply because it's just one of those things that was super easy to kind of catch on back in the day when we first started taking measurements of the temperature of the environment and like what would cause it to rain and like why would you feel hot and sticky versus why is it really cold or really dry. So that's kind of where the basis of the humidity started coming about. And you would use these, dry bulb and wet bulb thermometers. You'd spin it around, and that would be a way that you would actually measure essentially the humidity, the difference in temperature. You would measure the evaporation rate, that sort of stuff.
Gotcha.
Yeah, so relative humidity is essentially, again, the water vapor that's present in the air dependent on the temperature. Absolute humidity, which is less talked about and less known, is the total amount of water vapor in the air, regardless of the temperature. So, just in general, right, 1 cubic meter of air weighs about 1.2 kilograms. It contains around 20 to 21 grams of water. That's absolute humidity.
Okay.
And that's at 23 degrees C. And so I don't know if you're sharing your screen.
Yeah. So I just shared it, pulled it up. Yeah. Okay. 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 So yeah. Okay, so I'm sharing for those of you that are listening on Twitter Spaces on the YouTube stream. I'm actually sharing a screenshot of something called a psychrometric chart. Psychometric chart. I'm a psychopath. I don't know how to pronounce that exactly, but basically it's showing us the relationship between temperature and how much moisture is in the air. And why is that important to know, Andrew? So like, how does this relate to my filament and it's the danger that I face as a 3D printer?
Magic number that floats around online. You can see on Prusa's website, on just very different filament manufacturers' website like Polymaker or Protopasta. Anywhere from 10 to 15% relative humidity is where some of those ideal numbers are, right, for your filament. And the reason why is they say that at these relative humidities you're able to maintain the purity, if you will, of your filament. So water isn't going to impregnate the filament and isn't going to cause issues. So relative humidity, it's the problem with it is it's a relative term and it's completely dependent on temperature. And I kind of want to go through a thought experiment here with you. So at 40 degrees Celsius, at 100% relative humidity, 1 cubic meter of air can hold around 46 grams of water, right? Now, at 1 cubic meter of air at 23 degrees Celsius, like I said, it's around 20 grams, 21 grams of water. So if we were to take two containers, let's say container 1 can hold 46 grams and container 2 can hold 20 grams.
Okay.
Let's say that container 1 is at 15% relative humidity and container 2 is at 35% relative humidity. Well, container 1 and container 2 hold exactly the same amount of water. It's 6.9 grams. But container 1 has a significantly lower relative capacity. Well,
Okay.
It makes sense because if container 1 can hold 46 grams and you're only using 6.9 grams of its total carrying capacity, then you're only at 15% capacity, right? Container 2, it can only hold 20 grams. And if you're at 6.9 grams, you're at 35% of its capacity. Does that make sense?
Yeah. Yeah.
So this is where relative humidity actually starts coming into play. Now, container 1 and 2, let's say for instance we're going to change it to be exactly 35% relative capacity now. So container 1 will hold 16.1 grams and container 2 will still hold the same 6.9 grams. So container 1 holds 2.3 times as much water as container 2, but it shows the same relative capacity. So when we're talking about relative humidity, it's not just a number that's important. It's also a temperature. And most people don't actually think about that because they just think, oh, hey, I'm concerned about my relative humidity. Now, yes, relative humidity does give you a good understanding of how much water is in the air if you factor in the temperature. And it's that how much water is in the air, is it capable of actually removing or adding water moisture to your filament? So at room temperature, right, at a 10 or 15% relative humidity, there's a lot of headroom for, moisture to exist in that, cubic meter of air, let's say that container, right? But at let's move down to, 5 degrees Celsius, right? It's much smaller. And there's less headroom. So if you're still at 10 or 15% relative humidity, you actually have more humidity in the air, more absolute humidity in the air than you do at room temperature. Same thing goes for if you have, a higher elevated thing. So like a filament dehydrator, where you're running at like, say, 40 or 50 degrees Celsius, you actually have a much higher carrying capacity. Your container gets bigger. And that's how you're actually able to dry filament. Does that make sense?
It does, but it also makes me feel like relative humidity really isn't as good of an indicator of the threat to my filament as I would hope.
Yeah. And that's essentially what it is. And so I think it's somewhere in the noise, everything gets lost that, what actually is humidity? Like that's the issue I think that there's some misconceptions about. And humidity is actually free water vapor that's in the air. And, it could be, in just literally we're talking about molecules of H2O, like single molecules, but it could also be droplets, micro droplets, right? That consist of hundreds of thousands, if not millions of molecules. And this is what actually makes up the humidity and moisture in the air. And so when you start looking at relative humidity and see that it's so dependent on temperature, you're only getting part of the story. As another piece to this is understanding what is temperature, right? So temperature is kind of the average kinetic energy of the molecules that you're measuring, right? Everything in our world has temperature, right? And if we say something's at room temperature, maybe that's 23 degrees Celsius.
Yeah.
What we're basically saying is that at an average, these molecules have this sort of velocity or movement to them. And as you increase the temperature, you're increasing the movement and the velocity of these molecules. So in colder temperatures, the moisture and the molecules are moving much slower. In warmer temperatures, the moisture molecules are moving much faster. And this really comes into play when you think about how does moisture interact with everyday objects around us. Because, we have to look at how it actually gets into the air in the first place. And so if we imagine a cup of water, if you will, and you fill it up and you set it on your table, if you notice over a course of a day or so, the level of water will slowly decrease, right? Ever so slightly. And we know that is what? Evaporation, right?
Yeah.
Why is it evaporating? Well, it's because the relative humidity and the absolute humidity in the air is lower, right, than it can actually be. And so what you'll see is that these molecules will have enough energy, given their temperature, right, to break surface tension and to spontaneously leave the substance and go into the air, right? And this happens all the time. And so, over time, molecule by molecule by molecule, your cup of water is evaporating. It's going into the air. It's, dispersing throughout. Now, everything isn't a closed system, right? So if you had, a box around your house and it's hermetically sealed, well, eventually you'll reach 100% relative humidity and absolute humidity, and that everything will be in equilibrium giving on the temperature, and that glass of water will no longer evaporate, right? But since everything isn't in a enclosed system, there will constantly be, water that's evaporating and moving into the air.
Okay.
And so now that we kind of understand how water gets into it, how does water interact with all of these other molecules that make up, the world, right?
Yeah.
Well, so like I said, these molecules, they have a temperature, they have a motion, they have a movement. And so they're randomly moving around. You can, if you zoom in, right, atoms are so small. Like you cannot resolve an atom using light waves. It's too small, right? So we have to just kind of think about them. But they're really small, and air is a lot of empty space. And so these atoms are moving around, just bouncing around off of each other. They'll bump into other atoms, and they'll change directions. They'll change velocity. But there's an average overall movement, if you will.
Okay.
And this is known as kind of diffusion, right? So these molecules are leaving your cup of water, and they're diffusing into the air because there's a gradient. Right above the surface of the water is actually a higher relative humidity than outside of the glass of the water. Right. And this creates a gradient, and things flow from high to low. Right. And we know this as partial pressures. So as the water slowly moves up out of the glass and into the environment, it gets carried away. And again, as I was saying, it's bouncing off of things. Sometimes water will actually bounce onto something, a surface, and it'll stick to it. Okay. And why does it stick? Well, it's because water is actually polar. So water has this really interesting charge mechanism. If you look at the structure of water, it's kind of bent. It's got a hydrogen, an oxygen, and another hydrogen, right? H2O, and they form kind of a V shape. On one side of that molecule,
the Mickey Mouse, I like to call it.
Yeah.
Okay.
It's positively charged. On the other side, it's negatively charged, and these charges will actually facilitate it sticking to surfaces or other items or whatever it might be. And that's actually how you remove moisture from the air, and you again create another gradient. So
hold on just a second.
Sure.
So by gradient, when you're talking about, like, you're talking about these little, like, increasing domes of, like, moisture kind of propagating out into space. So it's not like immediately just shooting off to, like, wherever it can, but we create pockets of humidity. So that means that as you're closer to, say, the cup of water, you've got more humidity in the area surrounding, and then it'll move itself like a ladder up to the next and the next and the next, and kind of diffusing as it goes.
Yeah, and that process is actually really slow. So diffusion is a really slow process, but it happens, and it's constant. It's always happening around us, right?
Yeah.
And so how these gradients work is, like you were saying, they move from high to low. So if you have a high relative humidity on one side and you have a low relative humidity on the other side, it's going to naturally want to move and equal out, right? These are entropies, right? The second law of thermodynamics.
Entropy.
Yes. So,
the tendency toward chaos, though. Is this chaos happening?
Yeah. Well, so everything is everything wants to level out, right? Everything wants to be at an equilibrium. To remove that moisture from the environment is to create more order, right? And so you're basically creating less relative humidity, less absolute humidity, and so you have this little box, if you will, that has a lower entropy, right? And so you want to make it higher, right? You want to have chaotic distribution, so an equal distribution. Does that make sense?
It does. So let's draw it back for a second into. We know we kind of have an understanding of what's going on. The molecules are moving out. They're polar. They want to stick to different things. So in the case of air, that can be dust particles, that can be other things, but we don't necessarily need, like, we still get evaporation in a clean room, right? Like, just because there aren't things for the water molecules to stick through, they will move out into air.
Yeah, absolutely. And again, it's because air itself, while they're relatively the atoms that make up air are relatively stable. Again, water has, energy to it. And again, temperature is an average kinetic energy. So it doesn't really matter if you have an average kinetic energy at room temperature. There will be molecules that have higher than average higher than average measured kinetic energy, and they will break free from the surface and enter into the air, and then they will hang out in there because there's space, there's carrying capacity for that to exist. And, that's how it just moves. Like I said, you can have single molecules, or you can have massive droplets in terms of, molecule size, right? Hundreds of thousands of millions of atoms large, right? But these things are so small, you still can't even see them. Like, but that's really how it starts forming. And then once you have this in the air, it wants to stay there, but things will cool down. It will lose energy. It bumps into other atoms, molecules. It transfers some of its energy, and eventually it might land on something. It might bump into a molecule at just the right area direction, orientation, that it sticks, right? And so this is where we can start talking about, how does filament absorb or adsorb, right?
Oh, now what's the distinction between an adsorb and an absorb? Like my abdominals and my addition, right? So AD or AB, right?
Yeah.
This is an important distinction that I feel like it was not clear to me for a long time.
Yeah. So most people, they'll commonly say, "Oh, my filament is absorbing water moisture," right? AB, right? It's got too much water absorbed into it,
like a sponge absorbing water. Like that's what we think of.
The big misconception is actually it's not a sponge that's absorbing water. It's the water moisture is actually sticking to the surface of the filament. Yes, when you zoom in on the filament, there could be micropores and structures, on the molecular level that allow water to get inside. And again, this is known as diffusion. Even though a part is solid, water moisture can still diffuse through a solid. It can still make its way through that filament, and that would be known as absorbing, right? So the water moisture would be incorporating into the mixture, right?
Okay.
But in a sense, still it's adsorbing. It's not becoming. It's still stuck to the molecules. Is not actually causing a chemical change or chemical reaction in that sense. But what it is most of the time is that it's stuck on the surface of your filament, so it's adsorbed.
We're adding moisture to the surface of our filament. Is basically what I'm thinking. That's how I'm. And if it was to absorb, it would be getting into the molecular structure of the filament. And
yes.
The distinction,
so the crystalline structure, the molecular structure, that sort of, yeah.
Okay. And is one worse than the other? Does one happen sooner than the other? Like what's going on there?
Yeah. So adsorbing is really what filament does, right? And this is water moisture that's in the air, and it's randomly moving around, and it will touch the filament. It will bump into the filament, and the filament will then hold on to it because it bumped into the correct orientation. Maybe in some future videos we can actually do some demonstrations and show that. But in theory, what happens is the water molecule, it's polar, right? It has a positive and a negative charge, and if it bumps into the surface of another molecule that happens to have a positive or negative charge, and it's just aligned correctly, well, what's going to happen is that water is going to form what's called a hydrogen bond, and these hydrogen bonds are they're weak bonds, but they're still strong enough where you can't rub it off with your hand or anything, right? It's not going to just knock itself off. Again, it's basically like an electrostatic charge.
So
right?
I can't just brush off my filament, is what you're telling me. I can't just wipe the moisture off. It's happening at a very tiny scale. Okay, all right.
Yeah,
so that to me suggests that there may be some hope, though, that maybe I can't brush it off with my finger, but maybe there's other ways that I can get that moisture off of there so that it doesn't translate into giving me a poor surface finish on my 3D print or something like that, right?
Yeah. So we'll explore that here in a second. But I think the more important aspect is to talk about once the water is on the surface, right?
Yeah.
This is kind of what we refer to as the potential for a danger zone, right? In that the water is now on the filament and it's stuck to it.
Okay.
Eventually, as it builds up and you get enough water on the surface of the filament, it will actually migrate through and absorb into the filament. Right? It'll start to incorporate itself into the structure of the filament because again, these things are polar. And if you look at the structure, a cross section area of your filament, right? There are a bunch of other molecules that are also polar in the filament, and they naturally want to be balanced as well. And so the pull creates a gradient, right? So at the core of your filament, it has a less relative humidity, a less absolute humidity, right?
Right.
And so it wants to pull itself in. So what you'll see is over time, right, over a long period of time, the water moisture will slowly be incorporated into the core of the filament, and so that's where the danger zone actually starts happening.
Danger
So
zone.
yeah. So in terms of the water moisture that's stuck onto the surface, right? Drying your filament using desiccant or using a filament dehydrator, that's the easiest moisture to remove. It's also it also happens the quickest. If you raise the relative humidity carrying capacity, or I'm sorry, you lower the relative humidity, you increase the absolute humidity carrying capacity, right? You go back to our psychometric chart,
Yeah.
you will eventually start removing some of that moisture, right?
Okay.
By breaking those hydrogen bonds, because there's a higher affinity for the water to leave the surface of the filament and go into the air, right, or the medium, whatever it is that is around your sample.
Water decides it's got a better place to be than on your filament, so we're trying to give it a
Yes.
better option. We're not
Yes.
creating or destroying moisture. We're just giving it a better option for somewhere else to be.
Yeah. So in terms of drying your filament, like this is the easiest method, right, and or the best possible scenario. In that your filament will dry relatively quickly. You're not going to see any changes. You're not going to see any degradation of the product itself because the water hasn't made its way into the core of the filament and hasn't actually started to expand or break apart crystalline structures, of the filament itself.
Yeah.
Where it gets kind of scary is when it starts to absorb into your filament. You got to make room for the water, right? And sometimes when you're dealing with highly crystalline structures, the water will, fit perfectly nicely inside a crystalline structure. But then it's really trapped in there. Like you have a lot of different. You might have a positive hydrogen bond, and the oxygen molecule, with its negative charge is kind of up next against or in the crystalline lattice where it has a negative bond to another hydrogen molecule that has a higher positive bond. So basically it's locked in multiple ways, right? And it really finds this nice equilibrium. And so as you start charging, or as you start, building up, the more and more higher moisture content, the bad things start happening. You can actually start to split crystalline lattices. You can start breaking it apart. You can start degrading the polymer itself. Let's say, for instance, when you start 3D printing with a very wet filament, it will actually start, if you start heating it up and there's water moisture inside your filament, you can actually add too much energy to it that it'll actually escape violently and it will cause molecular cleaving. So it'll actually break apart other molecules because it has enough energy and it needs to get out. And
that sounds scary.
It expands like in steam. Yeah.
Molecular cleaving. That's a fantastic term. So it's an explosive release that will actually destroy parts of your filament. Is that what's making my filament brittle after a while? Like, am I experiencing cleaving?
Yeah. So that's exactly it. So as the water moisture gets in, you're actually, causing things to expand. There's a lot of different things, right? This is just one of those.
Okay.
But you're causing degradation of the polymer itself. These polymers are really long chains, and they're quite strong, but they also gain their strength because of the interactions with the other polymers. And when you start forcing them apart or you start causing the expansion to happen, you can actually cause these things to, start moving, right? Again, we're talking very, very small movements here, but it's degrading the structural integrity of the mixture or the crystalline structure, of the polymer itself. Does that make sense?
It does. So you mentioned silica or desiccant specifically, and it is a very common, when we get our filament, it has that little satchel, whatever you want to call it, sachet of desiccant in it. supposedly to basically give moisture a place to go instead of into my filament, right? Now you'd mentioned or you'd said something earlier that kind of struck me when we were talking about drying. Like, does desiccant actually dry filament though?
So it does and it doesn't. What it does is it creates a place that has it has a higher affinity to absorb water, right? The moisture out of the air.
Okay.
So again, what you're doing is you're creating essentially a gradient. So we have desiccant, whether it's molecular sieves, whether it's silica gel. We have basically a structure, a chemical structure that has a high affinity to hold on to water moisture because it in itself is polar and it has a lot of surface area. And so once water touches it, right, it gets stuck to it and it doesn't let go.
And that's the term we hear, hygroscopic or hydroscopic. Like that means it has an affinity to grabbing onto moisture.
Yeah, correct. Yeah, so it has an affinity to grabbing on and holding on. And so, silica gels or molecular sieves, they're hygroscopic. So that once a water molecule will touch the silica gel or, whatever it is, it will actually get bound to it and forms these hydrogen bonds. It adsorbs onto the surface. Okay. Right? Now, molecular sieves and silica gel, they're incredibly porous, right? It's made from a powder that's compressed. So there's a bunch of pores and it can absorb, right? It's like a sponge. It will make its way into the core of the gel or the molecular sieve. And it does a really good job at holding on to, this water moisture. And so again, what you're doing is you're creating a gradient, if you will. Now, this gradient that you're creating, it's a diffusive gradient. So water molecules have to diffuse through the gradient, right? They have to naturally travel, into the silica gel or the molecular sieve. And eventually what will happen is you will reduce the overall relative and absolute humidity of the container if you're talking about a sealed environment, right? And in that aspect, you can start to dry filament. But there's usually always a limit, right?
Yeah.
If you're able to remove it down to 0% relative humidity, 0% absolute humidity, then yeah, in theory, if you were to increase the temperature or whatever, you could start breaking some of these hydrogen bonds on the filament. It will start making its way off the filament into the silica gel, right, or into the molecular sieve. But this process is really slow. Again, because you're dealing with diffusion content, diffusion actions, right? And diffusion is very, very, very slow. Maybe in another, episode, we could actually go into some of the diffusion laws. We can, talk about Graham's law and Fick's law about diffusion and really kind of analyze, maybe even do some math and show the process and how kind of slow it is. But yeah, in theory, silica gels can be used to dry filaments, but the best way to look at silica gel is a way to retard the ingress of moisture into filament, right?
Okay.
So every time you're going to open up a bag or your storage container, you're going to let high relative humidity air into the environment, and you want to make for sure that as those molecules bounce around, they're typically going to have a higher affinity to bounce around towards your silica gel or your desiccant instead of sticking to your filament, right?
Yeah.
And that gets into the water activity constants of the actual material itself, right? So humidity is it's a partial pressure, and some might remember that way back in like high school chemistry. But partial pressures exist everywhere. Like I said, there's a partial pressure just above the surface of your cup of water that evaporates. There's a partial pressure of essentially the water on the surface of your filament.
Okay.
And so you're basically trying to reduce those partial pressures and make things have a higher affinity. And this is known as kind of the water activity index of material, right?
So let me ask you something really quick, because I think this is a misconception that I had for a long time. I wanted to think of like, okay, we've got a bag or a box or a container, if you will, and it's got my filament in it and it's got some desiccant in it. Okay. Mm-hmm. And I was thinking for a long time, like, is the desiccant, because it's got more of an affinity for water, like, is there a magnetism? Like, I wanted to think that there was this like magnetic draw or something that was like pulling the moisture more towards it versus the filament. But it sounds like that's not a great analogy necessarily, because there's no actual like pulling that's going on, we're hoping to increase the odds of the molecules like bouncing or bumping into the silica
Sure.
before they bump into my filament or something. Is that right?
Yeah, so in theory, there is a slight pulling action, as I mentioned, right? You're creating basically a gradient.
So if
A
you're
low
within that
relative-
gradient, there's a pulling action, but the further away you get, the less likely you are to be around where it's.
Exactly.
So you need it close. You need it really close, is what you're saying.
Yeah, you need it close. And the best thing that you can actually do when it comes to drying filament, if you're going to use a passive system, is to increase the movement of the air, right? The movement of the medium. This gradient, it exists, and it exists on a very, very, very small scale, right? We're talking, like literally molecule lengths long, nanometers, maybe at best. And, again, it slowly creates this natural pull because, again, humidity wants to, or just in general, entropy wants to move from high to low, right? Or, we want to equal out, right?
Yeah.
And so, basically you can think of it in a sense that it's a slight magnet, but it's a very, very weak magnet that decreases exponentially the further and further you go away. And then this is where you start dealing with Brownian motion, right? So the random motion of the molecules inside your container. And, it becomes a statistics problem, right? You want the molecules, the water vapor molecules, to bounce and touch the silica gel or the desiccant, whatever it might be, more often than the actual filament itself, because the filament will still always have some affinity towards holding on to that moisture, right? And if the moisture touches the filament in just the right way, well, it's going to get stuck probably until it gets enough energy to get knocked off. Maybe another molecule hits it. Maybe again, there's that overall gradient. It still will naturally want to hold on, right? So this is why drying wet filament with silica takes, well, for one, an incredibly long time, and two, probably shouldn't really be done. It should just be looked at as a way to basically retard the process of it getting wet.
So what I'm hearing, it does, and what I'm hearing is that silica is more a preventative measure than an active drying. So we're doing it to try to decrease the odds of those molecules bouncing around. And you said something interesting because I haven't seen this before, but it gives me some ideas for potential product development. Part of the reason I called you about this is because I'm interested in trying to improve the effectiveness of the products that I sell and stuff like that. And I get asked all the time, like, when are you going to put a heater in this thing and all that stuff? And I'm like, well, I could do that, but are people going to want to pay for it? Is that practical? Does it really work? Like, what's the best bang for your buck? There are other solutions like that we can do. But just to go back to the idea of the fan really quick, we talk about the statistics problem. We're trying to increase the odds of the moisture going to the desiccant over my filament. Adding some circulation, is that expanding the gradient? Is it helping to do that? Or is it more pushing more molecules toward the gradient that we're doing?
Yeah, it's literally pushing more molecules towards the gradient. You want to have the most molecular interaction you possibly can, right? And so by stirring the pot, you're moving and mixing all of you're moving and mixing all of those molecules together, and you're increasing the odds at which they're going to bounce around and get absorbed, right? Now one interesting experiment, and this would be fun to show in a live demo, is actually taking some salts like lithium chloride. I actually have some, maybe sometime next week or whatever. I could bring some up. And I can show that lithium chloride, it's a salt. It has this incredible ability to pull water moisture from the air. It creates a very strong interaction. If you were to store lithium chloride in an enclosed container at a saturated solution, it's actually a test index for calibrating hygrometers. And you can get around 10% relative humidity at a room temperature. But it's really cool because over the course of like 20, 30 minutes, you can actually watch this lithium chloride go from a white powder to kind of a soupy mix because it has a really strong affinity to pulling moisture out of the air.
Oh, that's wild. I want to show that. So it's literally just sucking up all that moisture. So it's a very, very strongly hygroscopic material. Very, very. So it's got a bigger gradient, a more surface area. And is it absorbing? Is it adsorbing? I mean, I guess everything kind of does a little bit of both, but.
Yeah, it kind of does both, right? So, like, where you start getting into the interesting things with adsorb and absorb. A lot of times in biology, you refer to it like as absorbing. It's being incorporated into a cell or the cellular membrane. Whereas, adsorbing, it creates these hydrogen bombs that just kind of sit on the surface. Where it kind of, the gray line comes is when you have, like a molecular structure, like a crystalline lattice or whatever, and that water, is it just on the surface? Is it surface moisture, or is it bound to moisture, which is bound inside, and it is absorbed in? So in this case, it's both, but it's still functioning off the basic principle of adsorbing, right? So the water molecule hits a molecule, and it has this really strong affinity to grab onto it. So you have these these desiccants, if you will, that have a really strong affinity for holding on, and you can create larger and larger gradients, right? And you can literally watch it as it pulls in this moisture from outside. You could go to your local hardware store and you can buy these damp rid containers, and essentially it has a salt. And that salt pulls in the water moisture, and then eventually it collects inside the cup, and you end up with like a whole bucket of water at the end of the day. So it's kind of like it's like that process of the molecules are randomly bouncing around. They'll hit onto a surface, and they'll have a natural affinity, and they'll grab onto it, and they'll stay. They're stuck.
So again, let's try to draw it back to the 3D printing. I wanted to go through a couple of questions that I had originally approached you with, just that I guess it almost sounds silly because it's like, I've been doing this for a while, but I feel like I'm still such a noob at understanding what's happening and what I need to do as somebody that's into 3D printing to increase my odds of success. Now, obviously, there are tons of different types of plastics and filaments that are out there, and some of these are way worse than others, right? We hear like nylons are notorious for soaking up water like a sponge, and that I've always been told, like, no matter what, you really always want to be drying your nylons and stuff like immediately before you're printing. Like there's limited stuff you can keep it sealed and all that stuff, but for the best results for some of these things, you just always want to really knock all those water molecules off of your nylon as quickly as possible. We, as hobbyist 3D printers, probably most often deal with like PLA, which is a cornstarch based product and stuff like that. And is that as bad as nylon? Like, is it really not that bad? Like, what's been your experience in terms of like how much moisture is really affecting it, and is it killing my print?
Yeah. So PLA itself doesn't actually have a strong affinity towards moisture.
What?
Which it's kind of interesting, right? So I've
been lied to.
I actually sent you an Excel document. If you want to share that, it's kind of neat. So we can kind of talk about it.
Really quick viewer note. I'm going to pause for a second. I am going to share that doc after the fact in the description and whatnot. I had learned early on that apparently we lose audio source when I do the screen share. So that'll be something we work on for the next time, and we'll do a little bit more testing ahead of time because I think the conversation's a little bit more important. But why don't you give us just a high-level overview of it, and I can...
Great,
you have it in front of you, so you can speak to it, but basically explain to people that are just listening what you tested and what you found.
Yeah, absolutely. So what I'm going to do is I'm going to switch my screen over here, and I'm going to show you guys. Hopefully this is coming through.
We can see and we can hear that. Okay, so maybe this is a good way to... Well, we have a workaround for you guys here.
Yeah,
and
absolutely.
Apologies for my Twitter folk that can't see this, but we're just going to describe as best we can what's happening.
Yeah, so what we have here is actually a moisture analyzer. Tom Sandlatter did a really awesome video about trying to show how much moisture is actually in filament. But
yeah, he did.
Unfortunately, he was kind of limited to the technology that he had, right? So what we have here is a lab, scale, essentially. It's a piece of lab equipment. it is a moisture analyzer. How it works is it's got a very sensitive balance in it. It can measure to 0.001 grams, and this is an actual balance. This isn't like a joule scale you buy on Amazon. This has a weight balance in it using really cool like just geometry and how it actually senses. It's awesome. You should look it up if you're interested in it.
It's on my Christmas list. It is. Hey guys on YouTube, real quick. I went to full screen, so hopefully you guys can see this better. Hopefully, is the audio still the same? Give me a thumbs up in the chat if you can, real quick. Keep going, Andrew.
Yeah, so this is a really cool piece of equipment. It basically can take a sample. So what I'll have here is actually a sample of NatureWorks NGO resin 404 3D. This is extruded and 1.75 millimeter filament. This is a 45 gram sample. And
that's PLA. So for people that don't know, NatureWorks is the ones that create the resin that is PLA generally.
Yeah. So you basically could take it, you could put it on the scale, and from there you then close the unit. And then it will actually go through a process where it will then slowly heat up the sample using a drying sequence, and it constantly measures the sample weight. And over time, it will plot this out over time. It will give you a drying rate. It will give you an overall moisture content, of your sample. So what I've done is I've actually taken a bunch of samples and I've started testing them, and I have some really cool results to show. So from the raw resin, so we actually source NatureWorks resin directly from NatureWorks, for some projects that we work on here internally at 3DGloop. So I actually have some resin that's unopened from them, so I decided to test it and see what their moisture content is. So their moisture content ends up being around 0.12% directly from the manufacturer.
0.12.
To put that in perspective,
yeah, okay.
Yeah, 0.12%.
Okay.
To put that in perspective, that's 1.2 grams per kilogram of PLA, right?
1.2 grams. So for every kilogram of PLA, 1.2 of it can be
would be water.
Water, okay.
Yes. So that kind of gave me a baseline, right? So then I said, well, I'm curious to see how much water moisture is actually in a brand new roll of a filament in a good vacuum seal from a reputable manufacturer, right? That has, been, really, really good. So the sample came back and it had 0.183% water moisture, right? And, I've ran this test several times and they kind of all average out.
Okay.
But yeah, so that's about 1.827 grams per kilogram, right? And that's straight from the manufacturer, right out of the vacuum bag with the desiccant in it, right?
Okay.
Which kind of tells me, okay, yeah, this is kind of a baseline, if you will, of, brand new filament. Let's just kind of count that as a baseline. So then, let's take a look at some other filaments. So I have and I'll show kind of on screen here. So this
show us some stuff, which we're not seeing much happening here. So this is the
resin, right? This is the resin, the raw resin. And my machine gives these little printouts, and you can kind of see the overall drying. It takes around 2 hours for it to actually completely dry.
So these little pellets here are what ultimately will become extruded and become the filament. And I apologize if that's too rudimentary for a lot of people, but I don't know that a lot of people have had the opportunity to see raw resin before. So that's interesting.
Yeah. So this is a 6-month sample, right? So this is a sample that's been sitting on a shelf for 6 months, not properly stored, nothing.
Just out in the open.
Just out in the open.
What kind of humidity? Where are you? Tell people where you are and what kind of humidity.
I'm in St. Louis, so we get a wide range of humidity. Most of the time, I think average is somewhere around 50 to 80%, just depending on the time of year.
Okay, so swing.
Yeah, it's Midwest, very humid, right? It's terrible in the summer.
So what happens with that degree of humidity? That seems pretty standard for a lot of people. So when you found that it's just been sitting out for 6 months, you said, what did you find?
Yeah, so 6 months. So 6 months improper storage. I saw a 0.271% moisture content. So that's 2.7 grams of water per kilogram of PLA.
And it was a 0.2 increase from the baseline when you first got it?
Well, yeah. So to give you the idea of the increase, so we'll take this and we'll subtract this from our baseline at a brand new, it's 0.88% or 0.88 grams more per kilogram, right?
Okay. Doesn't seem
So
like a lot.
not much, but this is where you're actually probably going to start seeing some stringing and wisps and that sort of stuff forming on your PLA.
After
Once you
6
start,
months, it took 6 months for it to get,
around 6 months,
and
right?
you'd say that's where you start to see degradation.
Yeah, that's where you can start to see the filaments getting a little brittle. When you start like bending it, it's not as flexible, ductile. Again, these aren't as accurate as I'd like them to be. I have a whole testing procedure planned out, so I'm going to be using this machine. I hope to have a really cool like big old Excel file with all the data. And trying to do a little bit of blind study too, just to make sure there's no bias.
Yeah. Switch back to your other. Switch back to your other camera now, if you wouldn't mind. Yeah.
Yeah.
Unless
sure.
you're not actually going to weigh anything at this moment, right? I think that's a new piece of equipment.
No. So so at 1 year, right?
Yeah.
We had this is crazy, right? We had a 0.459% water moisture. So that is 4.59 grams of water per kilogram of PLA. That's substantial, right? This is where the filament is very brittle. It breaks. It's not easy to handle. And it also, you can hear popping, cracking. This was 1 year of improper storage.
Just letting it sit out for it. So you have maybe 6 months before you start to see some physical. I mean, and that's obviously an average, and there's other contributors and stuff to it and stuff. And it makes no mention of like, how long has it been sitting on a shelf in the bag, from the manufacturer between that point that it was extruded or was even raw resin? Because every step along the way, that resin has an opportunity to be absorbing moisture, right?
Yeah, absolutely. And so then, I said, okay, well, hey, I wanted to see a 12-hour submerged sample. So let's take a sample of PLA and let's put it into water and let's submerge it for 12 hours. And so that sample gave us a water moisture content of 0.32% or 3.199 grams per kilogram of PLA.
Now, this is really an interesting point, and this is actually Andrew's looking off screen at the chart that I'm going to share a little bit. I can't do that right now because we'll lose audio. But that is a really interesting point because you're saying like it was literally submerged in water, and over the course of 12 hours, it gained 3 grams of mass per kilogram.
Per kilogram.
Per kilogram.
Yeah.
Per kilogram. Three.
Yeah.
Okay.
So what's interesting there though is the and I need to incorporate the drying sequence but into that Excel document. This was just kind of the summary of numbers. What's interesting is that 1 year sample took the full 2 hours of actually drying in order for it to hit an equilibrium weight. So it took 2 hours for it to finally hit steady state where there was no more moisture coming off the system. For the 12 hours submerged, right, it actually was dry in about an hour and 15 minutes. And the reason is because that water moisture that was on the filament was actually just stuck to the surface because we submerged it. It didn't have a chance to diffuse through the material, right?
So still plenty recoverable. Okay.
Yes, and so what was interesting is that the submerged sample is still completely ductile. It doesn't bend or doesn't crack. It doesn't break. It's just like normal filament. It's just wet.
So it can be subjected to moisture, but it's not until we hit the absorption point that we start to really see physical properties, molecular properties changing that are affecting our prints.
Yeah. That's basically it. So it's really interesting to start looking at this and just kind of collecting the data and just showing some of the general misconceptions that your brand new roll of filament, right? It already has moisture in it. It has, a little bit more than the resin that I measured, and this was literally out of a vacuum bag, perfectly brand new, right?
Yeah.
And then 4 weeks, just exposed on the printer for 4 weeks. It looks like it gained, let me get you the number here for how much it gained. Let's see, brand new filament. So it gained 0.043% water moisture in 4 weeks.
Wow. So
Like
what's
0.043%.
That's nothing. So
It's
drawing out your submerged test like Tom Sandlatter did, and like what's the comparison in terms of like how long do I leave it out in just the general open to get to that degree of saturation?
Sure. Yeah, so I think you have. I mean, everything's going to be. There's so many different factors. I can't
A lot
give
of
like a
variables.
general thing, right? But I would say, generally speaking, right, in 4
your
weeks of it
environment.
sitting, yeah, in 4 weeks of it sitting out, you're really not going to notice anything different. Again, most of the moisture is going to be adsorbed onto the surface. And as you're printing, you might see surface artifacts a little bit more because it might just start making it in very so slightly, into the actual structure of the filament on the outside. But generally speaking, you're really not going to notice that much of a difference. At least I haven't. And I'm printing on Prusa i3 Mark III's, and I don't notice any different from a PLA that's been sitting out in an unprotected environment for 4 weeks versus a brand new roll. In fact, I haven't seen any difference in 2 months, so 8 weeks. Around 6 months, I would say the 6-month sample, you can start seeing some stringing and wisps and that sort of stuff. And yeah, that's where, it's like, okay, maybe, if you're going to not print with your filament for, a couple weeks, put it in a bag. But if you don't, it's not going to be the end of the world. If you're going to not print with your filament for a couple months, maybe, yeah, you should definitely store it in a desiccated bag, just to make for sure that you're maintaining what that moisture is. And generally speaking, as long as it hasn't been left out for a very long period of time, most of the time it's going to be recoverable.
Yeah.
Because it hasn't actually gotten into the core of the filament. But in some cases, it depends on the manufacturer and the additives, because additives actually play a big role in how fast the material is able to soak up moisture. Because when we talk about adding colorant or, let's say carbon fiber or whatever, we're adding impurities into the crystalline structure. And now we have transport mechanisms. So water moisture is able to get deeper into, because there might be gaps in, the structure or, just the amorphous, globs of the, of the molecules.
Wait a minute. So what you're telling me is that different types of PLA, even so, whether I'm dealing with carbon fiber, reinforced, or even different tints, different colors, are some are worse than another. Like, what's the worst color for moisture absorption? Do you know that?
So there's so many different factors, and it's not saying that all color or a specific color is going to be worse than another, but generally speaking, right, if we think through it logically, if we have a PLA resin and it's homogeneous, it's pure in this sense. The moment we start adding color to it or any additives, it's no longer homogeneous. We can mix it up and we can call it homogeneous because it's equally mixed, but the fact of the matter is that these structures are just added into as a filler, if you will, to provide color. Yeah. And there can be defects. PLA is semicrystalline, semi-amorphous. So there will be areas where the PLA is in a crystalline, rigid structure, and there will be areas where it's completely amorphous. And you add colorant or additives to this, you're going to disrupt that distribution. And some of these additives can have higher affinities for grabbing onto moisture and holding onto them. And they can act as transport mechanisms to pull in the moisture further and deeper into the core of the filament, which then could lead to issues in the structural integrity.
Wow. That's interesting. So
yeah. These are
and
small...
we as consumers have no way of knowing. We're just thinking, oh, they added a little bit of dye in there, and really, I mean, is it still kind of generally negligible, or are you telling me like my orange filament is way worse than my black or my clear or whatever, or it just depends on what they're actually using for their colorant?
It really depends. And there will be some that are measurably worse than others, but I wouldn't say that it's like, okay, orange or yellow is the worst out of all. Like, for instance, like, we're working on some filaments and we have a purple color, and the purple color is anywhere from 4 to 6% by weight of PLA. So 4 to 6% of that PLA that you're printing is actually pigment, right?
Okay.
Depending on the color, there are some yellows or oranges that go up as high as like 10. Some reds even can go up to 15%. And so when you start, talking about colored filaments, they can actually have, a significant portion of additives that have higher affinities towards grabbing moisture and incorporating them in. So yeah, it's one of those interesting things, and I think it might be fun to explore that in future episodes.
So, and I think we will, and you bring up a lot of things that we didn't even touch on, like what are the crystalline structures? Like I really would like to be able to go deeper, but obviously we need to keep this at a reason. We're already at an hour, so I think I want to start trying to wrap up. But to be clear, in terms of like what we talked about today, is what you're advocating for? Like, do we not need? Are you putting me out of business? Like, do we just not need to store filament in a container? Or does it really not matter? Like, I don't think that's what you're telling me.
I think the underlying thing is that it really depends, and I don't think it's as important as a lot of people like to let on to be. It is important. You can have noticeable differences with filament getting wet. Obviously, it's empirically, driven, right? You can have a wet filament and you can see it prints like crap, and you can have a dry filament and it prints great. So there absolutely is a need to keep your filament dry. There's absolutely a need to, maintain your filament. But I think some of the misconceptions come in when you start looking at, what actually is relative humidity and why do we try and make such a big deal about it? And in reality, it's not so much just the relative humidity, it's the temperature, it's just the general, randomness that is the universe itself, and the affinity of water to, infect everything. So
you're telling me this thing is really more to just give me a sense of trend, but not necessarily like the minute I cross over 20%, my filament is dead. Like that's not the case. In fact, that there's times where this can be for 50, 60%. And really, it's not even affecting because the moisture isn't necessarily getting to the filament. It's just talking about the general amount of moisture around everything, right? But it doesn't necessarily have to do with its propensity to sticking or jumping to any particular thing.
Yeah.
Statistics
again. What's interesting is like let's say for instance you wanted to take your rep box and you wanted to put it in a freezer, right? You're going to lower the temperature, you're going to lower the moisture carrying capacity of that air, right? You're going to slow down those molecules, and in theory, right, just put your filament on ice. Problem solved, right? There's no
filament on ice sounds like the ice skating sensation of the year. Yes, I love it.
Yeah. You just reduce the amount of moisture carrying capacity of the air, right? You reduce the relative humidity of the air, and just in general, there you go, right? Alternatively, you could heat up your filament. You can add a dryer in it, right? Like you're heating up your rep box, and you're making for sure there's a lot of air movement, and you're going to keep a lower relative humidity there, and in that aspect, you're going to be able to dry it. But you could totally take your filament and throw it in the freezer. The colder you get it, the lower the relative humidity is. Again, if that's all you're caring about, that's one other way of doing it. And I don't think people actually can understand that. And so I've done some tests on that too. Just a filament that you take that's wet, right? And you can throw it in the freezer, and it doesn't necessarily dry, right? But it does dry a little bit, and the relative humidity is lower. But the interesting thing there is the relative humidity. Again, this goes back to the analogy. The absolute humidity that it can carry is also lower. So the process of drying it, like I said, it doesn't really dry because it can't really absorb. It can't really take that moisture away.
Well, and the moisture has to have somewhere else to go, right? You have to give it. Yeah. So I think for next time, this would be a great, continuation. That there are multiple ways of creating mechanisms, either via heat or cooling, oftentimes, or using desiccants and stuff like that to actually remove moisture or do that stuff. So that's I think a good deep dive for the next time. I think the main point that I really wanted to drive home today, in conclusion, one of the things that I think that is commonly an issue for people that are new, especially to 3D printing, is there is this just inherent fear that the minute that I open my bag of filament that I am on the clock, and that when they experience print failures for the first time, filament is such the scapegoat for failure when there are hundreds of variables that go into getting a good, successful print. And the truth is, when you don't know a lot of that stuff, you don't even have a concept of what a good print actually is and what you're doing. So yes, it is possible that you have bad filament. And yes, we can see stuff, but sometimes, you can just snap off the outer layers and the stuff inside is fine. Or you can still print with better filament. There are mechanical failures that obviously happen that can contribute to a bad print. But is filament often scapegoated more than you feel like it should be as a chemist, as a scientist, in terms of like, it's actually moisture that's causing my print to fail? Yes or no?
Yeah,
right now.
I would say that a lot of people, like, they blame the filament being wet or whatever, and it's not necessarily that. Absolutely, filament can get wet. There are filaments like nylons and PETGs where water moisture is significantly, more important, right? For PLA, right? I mean, I think Angus did a video. Tom's done a video. Lots of people have done videos showing that PLA doesn't really react as that much to moisture. It does, but it's not something where it's crazy, right? Yeah. Where PETG or nylons, you can get some crazy stuff happening. So it's a mixed bag, right?
Yeah.
Absolutely, I think wet filament is blamed far more than it should actually be. I can't wait to show some of the other experiments that we've been working on with, perfectly tuned with saturated salt solutions of, filament stored in 20%, 30%, 90% relative humidity, and showing how long it actually takes for it to absorb that moisture. It's going to be interesting.
I really appreciate your time, to take it and break it down. And I know that we covered a lot of ground, and I apologize again. This is kind of our first attempt at doing this remote thing and doing the simulcast stuff. So thank you guys for bearing with us. I hope you guys found something informative. I think we've got plenty of opportunity to kind of pick up and dive deeper into other stuff. I will work harder at allowing ourselves some better visual aids and other things, so you're not just stuck watching the two of us. Unfortunately, we realized too late in the game that we were losing audio when we were toggling to screen share and stuff like that. So hopefully we'll iron down the tech a little bit further so that we can continue to bring these discussions to you, because whether or not you're just a hobbyist and want to get better prints, or you're just a fan of the science and stuff, or maybe you're doing product development like the both of us are, and you want to inform some better decisions for your products, I hope that there's some value there for you guys. So, Andrew, my friend, like I said, we've covered parting thoughts, and maybe what to look forward to for next time. You mentioned some experiments you're doing. Tease us with some other stuff you're working on, and maybe even how it relates to the science of gloop and what you're doing.
Yeah, sure. So one of the fun things that I think I'm most excited about is actually showing how long it takes filament to actually absorb that moisture, and then how long it takes for that desorption of moisture. And really talking about adsorption isotherms. So just showing the rate of change over time, and in doing so, showing it in different relative humidity environments. There's some really cool things where many people don't know this, but saturated salt solutions in enclosed spaces. So I mentioned earlier, if you have a perfectly closed system, you'll reach an equilibrium of water moisture. And there's ways of doing that when using salts like lithium chloride, potassium carbonate, even table salt, sodium chloride. So we actually have some of those going on where we're using an apparatus called a desiccator, and we're able to put the filament inside the desiccator and just wait certain time intervals, and then we can take it back to our moisture analyzer, and we can analyze and see how much moisture is actually adsorbed into the filament. And I think also just taking and looking at some more crazy and complex filaments like nylons and peaks and PEI, and just showing their interactions.
Yeah. Exciting.
Yeah, and I think also just showing and trying to talk and explain about just general science terms and whatnot. Like I'm I don't want to claim that I'm an expert. Like, I know enough where I think I can dumb it down. And I'm not trying to be, derogatory by saying that. I just break it down into smaller pieces that I think are easier to understand. Now, naturally, in that I'm glossing over a lot of some of the other complex science. So I do want to figure out a way how we can kind of incorporate some of that more complicated science in the nitty gritty. Moving forward, because here at Gloop we love science. Like everything we do is based on science.
I'm a little disappointed you're not wearing your lab coat right now, my friend.
I know.
How are we supposed to believe you're an actual scientist if you don't have a white lab coat? Silky white lab coat, as Kyle Hill likes to say. No, that's great. And really quick, like, how does this help you in developing Gloop and what you do? I mean, tell us about that part of it.
Yeah. So there are a lot of internal projects that we're working on. We're coming out with new products. So hopefully we'll have something new, coming out soon. But as a part of that, we have to look at just generally how polymers react, how they're actually made, how they're synthesized. One of the interesting things is we see this all the time. People like, oh, hey, your glue's not really special, or people compare our glue to just solvent welding, and you can in some cases, but what they don't actually realize is we actually synthesize our own PLA polymer, and we actually synthesize our own elastomers. And so hopefully in the future we can kind of shed some light on how we do that. It might be fun to actually show the synthesis of PLA itself, and the polymerization of PLA. And so, maybe that would be fun to explore. But just in general, understanding just how these polymers interact with each other, just generally how 3D printing utilizes some incredibly complicated science and chemistry, and it's made so simple. Like you can do whatever you want with 3D printing, and like the materials that are available are just amazing, and just like shedding some more light on some of that. And I think, kind of broadening essentially the community's understanding of the science, I think would just be fun, and it'd help us, I think, build better products.
For sure. Well, my friend, thank you so much. I know we spent a lot of time, but I appreciate your time today, and I'm really looking forward to more conversations like this. And thank you guys all for tuning in. And I like I said, I hope you guys learned something, and we will catch you for the next one soon. So, until then, have a great day, Andrew, and we'll chat soon, my friend.
Yeah, thank you.
All right. See you later. Bye, everyone.